Good morning, students. In this video, we are going to discuss about the encapsulating security payload (ESP) under IP security. ESP can be used to provide confidentiality for the message content, authenticates its data origin, connectionless integrity for the data, and anti-replay service, a form of partial sequence integrity, and a traffic flow confidentiality, a limited traffic flow confidentiality. The set of services provided depends on options selected at the time of security association establishments and on the location of implementation in network topology. ESP can work with a variety of encryptions and authentication algorithms, including authenticated encryption algorithm such as GCM. Let us see the ESP format, how the ESP format is going to be. The ESP format contains the following fields. Let us see one by one. Security parameter index, which identifies a security association of 32-bit. Sequence number, which increases a counter value monotonically. This provides an anti-replay function, also as 32-bit. A payload data, a variable bit size. This is a transport level segment for a transport mode or IP packet for a tunnel mode. This is protected by encryption. Padding. The purpose of padding is used to expand the plain text, which varies from 0 to 255 bytes. Pad length, which an 8-bit, indicates the number of pad bytes immediately preceding this field. Next header, has also 8 bits, identifies the type of data contained in the payload data field by identifying the first header in the payload. Example, an extension header in IPv6 or an upper layer protocol such as TCP. The next one, integrity check value. The integrity check value is a variable one, a variable length field that contains the integrity check value computed over ESP packet minus the authenticated data field. Usually it must be an integral value of 32-bit. When any combined mode of algorithm is employed, the algorithm itself is expected to return both decrypted plain text and a pass file indication for the integrity check. Let us see how this is going to be happen. For a combined mode algorithm, ICV that could normally appear at the end of the ESP packet when integrity is selected and may be omitted. Let us see about the top level format. As we discussed about the security parameter index, sequence number, payload padding, pad length, next header, and integrity check value, which have been shown in this format. Also, the substructure of an payload data, which is going to be shown in this figure. The substructure, which has when ICV is omitted and integrity is selected, this is a responsibility of the combined mode algorithm to encode within the payload data and ICV equivalence, means of verifying that integrity of the packet. Two additional fields may be present in the payload as seen over there. Then the initialization value IV and a TFC padding. The two additional fields, the initialization value and traffic flow confidentiality, has been shown in this figure. The initialization value, if is present, if this is required by the encryption or authenticated encryption algorithm used for ESP. If tunnel mode is being used, then IP security implementation may add traffic flow confidentiality padding after the payload data and before the padding field as examined subsequently. Let us see the encryption and authentication algorithm. The payload data, padding, pad length, and next header fields are encrypted by the ESP services If the algorithm used to encrypt the payload requires cryptographic synchronization data, such as initialization vector IV, then this data may be carried explicitly at the beginning of the payload data field. If included, an IV is usually not encrypted, although it is often referred to as being part of ciphertext. This ICV field is optional. It is present only if the integrity service is selected and is provided by either a separate integrity algorithm or a combined mode algorithm that uses an ICV. That means the ICV is computed after the encryption is performed. This order of processing facility rapid detection and rejection of replayed or packets by the receivers prior to decrypting the packet. Hence, potentially reducing the impact of denial of service attacks. It also allows for the possibility of parallel processing of packets at the receiver, that is decryption can take place in parallel with integrity checking. Note that because of ICV is not protected by encryption, a keyed integrity algorithm must be employed to compute the ICV. Let us see the next padding. What actually padding is? We are aware about that, which is required to expand the plain text. Actually, the padding field serves several purposes. We will see the services. If an encryption algorithm requires the plain text to be multiple of some number of bytes, example, the multiple of a single block for a block cipher, the padding field is used to expand the plain text consisting of the payload data, padding, pad length, and next header fields to the required length. The ESP format requires that the pad length and next header fields be right aligned within a 32-bit word. Eventually, the ciphertext must be an integer, multiples of 32 bits. The padding field is used to assure this alignment. The last one, additional padding may be added to the provided partial traffic flow confidentiality by concealing the actual length of the payload. This is a service or several purpose of padding which is used in the ESP. Next, to move on to the anti-replay service. A replay attack is one which an attacker obtains a copy of an authenticated packet and later transmits it to the indeed destination. The receipt of duplicate authenticated IP packet may disturb service in some way or may have some other undesired consequences. The sequence number field is designed to thwart such attacks. When a sender SA, when a new SA is established, the sender initializes a sequence number counter to 0 each time what a packet is sent to this security association. The sender increments the counter and places the value in the sequence number field. Thus, the first value to be used is 1. The anti-replay is enabled by default. The sender must not allow the sequence number to recycle past 2 to the power of 32 minus 1 back to 0. Otherwise, there would be multiple valid packets within the same sequence number. If the limit of 2 to the power of 23 minus 1 is reached, the sender should terminate his or this security association and negotiate a new security association with a new key. But because IP is a connectionless and reliable service, the protocol does not guarantee that packet will be delivered in order and does not guarantee that all packets will be delivered. Therefore, the IP security authentication document dictates that the receiver should implement a window of size W with a default of W is equal to 64. Let us see about those with a pictorial representation. The right edge of the window represents the highest sequence number n so far received from a valid packet. For any packet with a sequence number in the range from a n minus w plus 1 to n has been correctly received, that is properly authenticated. The corresponding slot in the window is marked. Inbound processing proceeds as follows when a packet is received. Let us see about this inbound processing. If the received packet falls within the window and is new, the MAC is checked. If the packet is authenticated, the corresponding slot in the window is marked. If the received packet is to the right of the window and is new, the MAC is checked. If the packet is authenticated, the window is advanced so that this sequence number is the right edge of the window and the corresponding slot is in the window is marked. If the received packet is to the left of the window or if authentication fails, the packet is discarded. This is an auditable event. Let us see about the service which is going to be provided by the anti-replace services. And further we will discuss the tunnel and transport modes of operation. Already we come across this transport and tunnel mode in the previous video, an introduction. Let us discuss about this transport and tunnel mode operations for the ESP. A transport mode encrypts and optionally authenticates an IP data. It can do a traffic analysis and it's an efficient and it's good for ESP host to host traffic. As well, the tunnel mode encrypts the entire IP packet and adds a new header for the next hop, and no routers on way can examine inner IP packets. And it's good for virtual private networks and good for gateway to gateway security. Let me discuss in detail about this modes of operation. The figure shows end-to-end authentication and end-to intermediate authentication, which connects the internal network and external network. Discuss about transport mode. As we already come across, transport mode provides protection primarily for upper layer protocols and used for end-to-end communication between two hosts. And encapsulation security payload encrypts and optionally authenticates the IP payload but not the IP address. And authentication header authenticates the IP payload and selects portion of the IP header.